All right, section 2.7, we're going to continue our discussion with related rates today, remembering that if two or more quantities are related, then their rates of change are going to be related as well. So we're going to see that relationship between multiple variables over time. So let's go ahead and jump into our examples here and see how these rates are going to relate to each other and how we're going to solve them. So the radius of a circle is increasing at a rate of 4 feet per minute. We're going to find the rate of change of the area when the radius is 6 feet. So what I like to do with these problems is go ahead and sketch out, draw out kind of a picture of what we've got. So we've got a circle. We know the radius is from the center out, and we know it is increasing at a rate of 4 feet per minute. So if we let that radius be r, if we're increasing at a rate of 4 feet, so increasing at a rate of 4 feet per minute, we know they're giving us a rate, and they're telling us that the radius is changing over time, and the rate in this case is 4 feet for every 1 minute. We want to find the area, or the rate of the area, so we want to find how fast dA dt is changing, or how fast the area is changing when the radius is 6. So we know also the radius is going to be 6. So we need a relationship between the area and the radius of a circle. We just happen to hopefully know that area is pi r squared. If we have a relationship between two variables, we also have a relationship between their rates. If I take the derivative of the area and radius equation with respect to time, I'll get dA dt equals pi as a constant, the radius r squared, the derivative of that is going to be 2 pi r, and the radius derivative dr dt. So I know that the area is changing equal to 2 times pi times the radius times the change of the radius. I want to know how fast that area is changing, so I'm looking for dA dt. We go ahead now and fill in what we know. So dA dt is going to equal 2 pi, our radius, which is going to be 6 feet. I'm going to leave my units, I'm going to just put my units way up there. And then my dr dt, I know the radius is changing with respect to time at 4 feet per minute. So I have 4, and I'm going to have 4 feet per minute up there as my units, just to keep them kind of out of the way. So I have 2 times pi times 6 times 4. 2 times 6 gives us 12, times 4 gives me 48 pi, and my units are going to be feet times feet per minute, or feet squared per minute. And that should make sense to us since we're talking about area changing. Area is going to be in square units per minute. So we know that the area is changing at 48 pi feet squared per minute. Very important that we remember our geometric formulas for area and volume and all those good things. So, in example 2, we have a spherical balloon, or we have a sphere. So I'm going to draw that as kind of in this fashion. And what do we know about the sphere? It is being inflated with helium at a rate of 400 cubic centimeters per minute. So if I inflate this, I'm increasing the volume. And they're telling us that it's increasing at a rate of 400 cubic centimeters. So it's telling us dV dt is 400 cubic centimeters for every minute. We want to know how fast the radius of the balloon is changing when the radius is 20 centimeters. So telling us the radius is 20. I'm looking for dr dt. How fast is that radius changing? Well, I know that this radius is 20, don't I? So I need a relationship between the volume of the sphere and the radius of a sphere. I just happen to know that volume is 4/3 pi r cubed for a sphere. If you're doing your note cards, you'll remember that as well. I can go ahead and now find the derivative with respect to time. So the derivative of v with respect to time is dv dt. 4/3 pi r cubed derivative is going to be 4 pi r squared. Take the derivative of an r, so we need dr dt. Now we can go ahead and plug in what we know. We know dv dt is 400. We have our 4 pi. Our radius is 20, so 20 squared gives us 400, and then dr dt. Go ahead and solve for dr dt. We can divide the 400 over, that gives us 1, then divide by 4 pi. So dr dt, ran out of room, I'm going to put it over here. Dr dt is going to equal 1 over 4 pi. Now what's our units going to be? Well, if we have cubic centimeters per minute as our volume, so centimeters cubed per minute, and we're going to go ahead and divide it by r squared. Our radius was 20 centimeters, so if I divide that by centimeters squared, I'm going to end up with centimeters per minute. And that should make sense to us, our units on that, because our radius would be in a single exponent. So it would be kind of a linear, if you wish, form. And that gives us our answer, 1 over 4 pi centimeters per minute. These problems can get lengthy, they can get difficult, they can get to be where you got to think a little bit. And in this example, we're going to see that. So a conical tank is 15 feet across the top and 10 feet deep. Water is flowing into the tank at a rate of 5 cubic centimeters per minute. Find the rate of change of the depth of the water when the water is 4 feet deep. So the first thing we should probably talk about is what a conical tank looks like. A conical tank is simply a cone. Something like that. In here we know that it is 15 feet across the top. So 15 feet through the center there. We know that water is 10 feet deep. So we're going to go 10 feet deep there. And if water is flowing into the tank at a rate of 5 cubic feet, we know the volume then, because we're putting water into it, that's going to increase our volume, isn't it? So dv dt is going to be 5 cubic feet per minute. We want to find the rate of change of the depth of the water when the water is 4 feet. So if we go from the center and down, we know our height is going to be 4 feet. So kind of our water line is going to be maybe in that form. So our height is going to be 4. We want to come up with then how fast is the depth of the water. We want to find dh dt. That's what we're looking for. So we need a relationship between the volume and the height of a cone. Anybody recall what the volume is going to be? Volume. Volume is 1/3 pi r squared h. So that gives us somewhat what we want. We have that radius and we have the height. We'd really like to get rid of that radius, wouldn't we? So is there a relationship between the radius and the height of a conical section, of conical tank or conical figure? And we do have one. If this is our radius and this is our height, we have a right triangle. And we have two similar right triangles. So we know that they're going to be proportional to each other. So my radius of the larger one is going to be 7.5, where my height is 10. My radius and my height at any given point in time. So I can go ahead and find a relationship there. I know the radius to 7.5 is going to equal my height to the height of the conical of the cone, which is going to be 10. So that's my relationship between r and h. So r divided by 7.5 is equal to the height divided by 10. I can go ahead and then solve for r. So r is going to be 7.5 h's divided by 10. If we come down to our formula, the volume is 1/3 pi, our radius squared, so it's going to be 7.5 h's divided by 10 squared times h. We can pull out that handy dandy calculator, take 7.5 and squaring it, we end up with 56.25. So our volume is 1/3 pi times 56.25 h squared over 100 times h. More importantly, we get rid of that r's, and now they're all in terms of h, which is what we're going to be looking for. We want to know how fast that height is changing. Anytime we can get rid of a variable, it's going to be a good thing. So we have 1/3 pi. We can go ahead and multiply those together. So we have, I'm going to go ahead and get rid of that. I don't like that. I'm going to bring this 56 1/4 out to the 1. So we have 56 1/4 pi's over 300. Multiply your denominators together times h to the 3rd. Now, I'm going to go ahead and find the derivative. My derivative with respect to time, dh dt, is equal to, multiply your 3 out here. We can go ahead and divide those 3's out. So we get 56 1/4 pi h squared over 100 dh dt's. We know the height is actually 4 units, don't we? We also know that the volume is changing at a rate of 5 cubic feet per minute. So I can go ahead, come off to the side here. So 5 is going to equal 56 1/4 over 100 pi times my height squared, which is 16, and then dh dt. I can go ahead then and divide all of this over, multiply by 100. So we're going to have 500 divided by, if I multiply 56 1/4 times 16, that's going to be a nice clean number, isn't it? It's going to be 900 pi. So we have 500 over 900 pi is going to equal dh dt. So if we go ahead and divide that out, clean it up a little bit, we have 5/9 or 5 over 9 pi. And our units in this case are going to be feet per minute. And that's going to be how fast our height is changing. The next one, the ladder problem. You're going to love the ladder problem. The ladder problem shows up pretty much everywhere. It's generally on a test somewhere, on a quiz, doesn't matter. We always probably see a ladder problem. So get used to it. Ladder problems are our friends. So let's go ahead and look at this ladder. We have a ladder, it's 15 feet long, is leaning against the wall of a house. So here's my house, here's my ladder, and it's going to be 15 feet long, so we have 15 there. And what's happening with this ladder? The base of the ladder is being pulled away from the house. So we're going to go in this direction at a rate of 3 feet per second. So that's giving us a rate. And if we're looking at a triangle, we can let this be, say, let's A. So that side length would be dA dt. So that's a rate of that distance changing. Part A says, how fast is the top of the ladder moving down the wall? So we're looking for this rate when the base is 9 feet from the wall. So we know that A then is going to be 9. Well, we know that this is going to be a right triangle. Very important that we have that because now we have a relationship between the 3 sides of a right triangle. We should remember that a squared plus b squared is going to equal c squared, where a and b are the 2 side lengths or the 2 legs, and c is the hypotenuse. We can go ahead and find the derivative of this in relationship to time. So we have 2a dA dt plus 2b dB dt is going to equal 2c dc dt. So we have a lot of variables in here that we've got to figure out what's happening with them. So what do we know? Well, we know a and we know dA dt, so we can go ahead and plug those in. We know a is 9 and dA dt is going to be 3. Do we know b? Well, if we know this is 9 and this is 15, we know that a squared plus b squared equals c squared, don't we? So we know that 81 plus b squared has to equal the square of 15, which is 225. Go and subtract that off, and we end up with what? 144. All b. So b equals a nice round 12, doesn't it? So we got our b value, which is 12. dB dt, we don't know what that is, so we're going to leave it as our variable, dB dt. That's what we're going to solve for. C and dC dt. Well, C is talking about the height of the ladder, which is going to be 15, and then dC dt. dc dt is talking about how fast this ladder is changing. So is it being expanded or is it being contracted? And it's not. It's just a nice ladder. It's leaning up there. So that rate is actually going to be 0. It's not changing at all. Now we can go ahead and solve for dB dt. So we have 2 times 9 times 3. So we have 54 plus 24 dB dt's is going to equal 0. Solving for dB dt, subtract your 54 and divide by 24. So dB dt is going to equal negative 54 24ths. And our units in this case are going to be feet per second. If you want to reduce that, you can. If you want to divide it out, you can. Personally, I'm going to leave it. Part B of this says, find the rate at which the area of the triangle created by the ladder, house, and ground is changing when the base of the ladder is now 9 feet from the wall. So again, same thing's happening, same setup. We're going to know that dA dt is going to be 3 feet per second, dB dt, and all this good stuff. So now, if we have our triangle here, we know that B is 12, we know that A is 9, we know that C is 15. We need a relationship between the area and the side lengths. So we know the area is going to be 1/2 of the base times the height. So we have 1/2 of B times little a. If you want to change these to h's, you can, so you don't get the a's mixed up. I use a capital A for area and little a for my side length. So we can go ahead and find the relationship between the rates. So dA dt is going to equal, well, here we have b times a, so we have a product rule. Product rule between b and a, we have b d little a dt plus a dB dt, sorry. So we want to know how fast the area is changing, so we're looking for dA dt. We have 1/2. Our base is going to be 12. dA dt, we know, oh, look at that, it's 3 feet per second, isn't it? Our A value we know is 9. And dB dt, we know, hey, it's negative 54 24ths. I guess I should probably go and reduce that then. So negative 27, oh, we can probably go further than that. Negative 27 twelfths, which we can take out a 3 as well, so negative 9 fourths. I suppose we should leave it like that, shouldn't we? So negative 9 fourths. Extended response, we could leave it like that, put our units on it, call it a day, or you can go ahead and figure that out. We'll go ahead and throw that into the calculator, I suppose. We have 36 plus a negative 81 fourths, and then we're going to divide that by 2, so we get 7.875. And in our units, in this case, we're looking at the area, and we're going to be feet squared per second. The next part of this problem, oh yes, we're not done. We're continuing, part C, so this would be a great problem, extended response, if you're looking at it, because it gives 3 different parts, and we have different things within that. So we're going to find the rate at which the angle between the ladder, so that's going to be interesting, between the ladder, here's our ladder, and the wall. So we're looking at this here. We'll call it theta. We're looking at the rate at which that angle is changing. So we're looking for d theta dt when that ladder, again, is 9 feet from the wall. So we could pull all that information from part A. Notice how everything's kind of building upon itself. So we need a relationship between this angle and the side lengths of our triangle, remembering that we have a right triangle. So there's a lot of different things that we can relate. We can relate this angle with sine, cosine, tangent, cotangent, secant, cosecant, any of the 6 trig ratios. I would suggest that we choose one that's going to work fairly easy for us. So how about if we let the sine of theta, and we'll talk about that, the sine of theta being the opposite side length, so not opposite, we'll leave it as O first, over the hypotenuse. If we go back to our values, we let this side be A, I suppose, and we let this side be C, so we should probably change this O and H into A and C. So let's go ahead and find the derivative then of this trig equation. So derivative of sine we know is positive cosine. Where did I get that negative at? Cosine of theta times the derivative of the angle, which is d theta dt. And that's going to equal, we have a quotient rule between a over c. So we have c dA dt minus a dc dt all over c squared. We're looking for d theta dt, so we can divide by the cosine of theta. So d theta dt is going to equal c. We know c. C was 15. dA dt, we know dA dt was going to be 3. Minus our a, which is 9. dc dt. dc dt, remember again, is going to be 0. It's not going to change. Divided by c squared. C was, again, 15. So we have 15 squared times the cosine of theta. Because we're going to divide by the cosine of theta. So the cosine of theta is the adjacent over the hypotenuse. Our adjacent was 12. So we have 12 over 15. We can go ahead then and reduce this. So we have 15 times 3, 9 times 0, that goes away. So we have 15 times 3 divided by here. 15s are going to cancel each other out, aren't they? So we have 15 times 12. Well, my 15s can cancel. And then my 3 over 12 is going to be 1/4. So we have 1/4. Well, what's our units going to be? Wait, what does theta talk about? Theta, remember, is going to be in radians. So we have 1/4 radian per whatever we have. In this case, it's going to be per second. And that's going to give us our angle change. I know it's kind of a lengthy process here today, but we're going to go ahead and do one more. It's kind of a fun one. I enjoy this kind of problem. We're going to find the rate of change of the distance between the origin and a moving point on the graph of y equals the sine of x. If dx dt equals 2 centimeters per second, when x equals pi over 3. Good gracious. If I look at the graph of this, sine of x. Oh, that's not the sine of x. Sine of x. Whew. Goodness, I was thinking cosine. I was thinking the derivative of the sine of x there. So here's our sine of x. We have x equal to pi over 3, so we're going to be about there. But more importantly, we're looking at this point and the distance we are from the origin. So we're looking at that there distance. And we know that this is the equation y equals the sine of x. So what's going on with this? Well, if we want to know the rate of change of the distance, we need a relationship for the distance and the x and the y values. Well, we do know that, don't we? The distance is the difference of the x's squared plus the difference of the y's squared. We know that one of our points is 0, 0. Our other point, in general, is going to be x sine of x. So we can go ahead and find that distance. The distance is going to be the square root. We can let this be x1 and y1 just because we're subtracting off, and subtracting 0 would be nice, wouldn't it? So we have our x value squared plus our y value, which is the sine of x squared. Notice we have it in one nice clean variable. We got rid of those y's. So now we can go ahead and find our derivative. So d capital D dt, which is going to be how fast the distance is changing, equals the square root of this. Our derivative is going to be 1/2. We have a nice chain rule here. So we have x squared plus the sine of x squared to the negative 1/2 times the derivative of the inside. Derivative of x squared gives us 2. Derivative of sine of x to the second. Oh, good golly. Yes, we have a chain rule. Another chain rule. So we have 2 sines of x to the first times the derivative of the inside, which is going to be a cosine of x. So that's going to be our derivative, how fast that derivative is changing. Oh, I didn't put my dx dt's in there, did I? Dx dt, because I took the derivative of an x there, and dx dt at the end of this as well, which is the derivative of my angle. Ooh, almost forgot that. I would have gotten yelled at for that, wouldn't I? All right, so we have a negative exponent. We can take that to the bottom. And we have our dx, or 2x, dx dt, plus 2 sine of x cosine of x dx dt, over our x squared plus the sine of x squared to the 1/2. Now we can go ahead and plug in what we know. We know that x is going to be pi over 3, and dx dt is 2. So we have 2 times pi over 3 times dx dt, which is going to be 2, plus 2 sines of pi over 3, cosines of pi over 3, times dx dt, again, which was 2, divided by x value, which is pi over 3 squared, plus the sine of pi over 3 squared to the 1/2. Now, here's the deal. Those of you that don't remember what the sine and cosine of pi over 3 is, or can't figure that out, we're going to leave the answer like this if there's no other things that we need. Unless it's asking for our units, which of course we should be able to put our units on this. So our distance is in centimeters per second. Now, we could leave this just like this if we need to, if you don't remember what the sine and the cosine of pi over 3 is. But remembering that unit circle, pi over 3 is coming up like this, so we know that our point is going to be here. We're coming over a little and up a lot, so we have 1/2 there, and our radical 3 over 2 is going to be there. So we have the point 1/2 radical 3 over 2, don't we? Remembering cosine and sine. So the cosine of pi over 3 is going to be 1/2, and the sine is radical 3 over 2. So if you're so inclined, you can rewrite this as 4 pi over 3 plus 2. Actually, we can do, we'll do 2. Sine of pi over 3, which was radical 3 over 2. Cosine of pi over 3, which is 1/2 times 2, divided by pi over 3 squared, plus the sine of pi over 3, which is radical 3 over 2 squared to the 1/2 power. From there, you can clean it up as much as you want. I'm going to kind of stop it there because I've run out of room, 1, and 2, it's just manipulations at this point. So there gives you an idea of where we're going to see related rates and what happens with them and how they all work. Good luck. If you have questions, don't hesitate to ask. Good luck.